Among the many masterpieces of nature, snowflakes stand out as one of the most elegant and unique. With their radial symmetry and fractal structure, even the simplest snowflakes are an example of simple mathematical ideas coming together in nature to form seemingly unreal patterns. Even though snowflakes can be considered fairly complex geometric structures, at the same time they are incredibly simple. It's easy to draw a snowflake if you just cross some lines and make them branch out as they get further from the center. With this project, I wanted to do something in between. I wanted to keep their apparent complexity while also displaying their simplistic side. My goal was to create an algorithm which mimics some of the ways snowflakes form and creates a unique one every time. When it comes to fractal shapes or any self-repeating patterns, it's hard to talk about them without mentioning recursion. To put it simply, a recursive function is a function which calls itself. Usually in programming, functions are structured such that the output of one function gets fed into another, forming a sort of a chain. With recursive function, instead of a chain, we are forming more of a loop. When looking at a drawing of a snowflake, we notice it consists of 6 identical parts. If we remove 5 of those parts, we are left with a pattern which resembles a tree, and trees are a perfect example of recursion. Let's imagine we have a branch, represented by this straight line. At the end of the line, the branch might split up into 2 smaller branches, and each smaller branch will split into 2 even smaller branches, and so on and so on. This can continue as long as we want. In this example, we can imagine a class called branch, which has a function called split. Each time a branch splits, it creates 2 more branches and tells them to split. Those 2 branches create a total of 4 more branches and tell them to split. This loop can go on until we decide to stop it, depending on the level of detail we want to achieve. If we then take one of those branches we created and duplicate it so that each branch starts from the same point, we have something that looks a lot like a snowflake. This is the algorithm I'm going to use to generate my snowflakes. We can begin by defining a snowflake class. This class will hold all the information necessary to create the child branches. The snowflake passes on the information to the first generation of branches, and then each generation passes on the same information to the next. For the branch, I'm going to create a class called snowflake segment, which contains the function called render segment. This is the function that will be used to pass on the information to newly created branches and render them on the screen. The first variable we need to define is arm count, which represents the number of initial branches we're going to have. In nature, this number is always 6, but since this is not the real world, we can afford some creative freedom. Next, we need a variable which keeps the number of generations we're going to have after the initial generation. For example, if this number is 0, there are only the main branches. If it's 1, the main branches will split once, and so on. Then we have node count. In the examples we've seen so far, the branches always split at the end point of the line. But we might want to create some splits before the end of the line, so we achieve this by creating nodes which can hold the next generation of branches. Another important variable is a length multiplier. Without this variable, all the child branches would be the same length as the parent branch, but instead we multiply the length by this constant, which goes between 0 and 1, making every generation a bit smaller than the previous. This variable also controls the length of the branches of the same generation as they get further from the center. Although in this case I also made it possible for the branches to increase in length instead of always shrinking. Lastly, we have a variable which controls how much the branches spread out from their parent branches. This is an angle which goes between 20 and 60 degrees. With smaller angles, the snowflakes are more tight and dense, and with bigger angles, the snowflakes span out and occupy more space. I'm now going to take all of these variables and make them parameters of the render segment function of the snowflake segment class. This function takes the angle parameter and applies the object rotation, applies the end point of the line based on the length parameter, and then calculates the node positions. It checks the generation's left parameter, and if it's greater than 0, that means that the current branch should split into smaller branches. This is where recursion comes into play. The function creates child branches and then calls the same function on them, passing mostly the same parameters. The parameter generations left is reduced by 1 every time a new generation of branches is created. This way, the function has an exit point and is not called in an infinite loop. In the snowflake class, I created this randomize values function so that every time a snowflake is generated, we get a different result. If I now run the code and generate some snowflakes, here are the results I get. As you can see, some of them are quite simple and some of them are more complex, but each one is unique in its own way.